Welcome to the fourth video of exponential equations, looking at exponential decay. In this video, we'll be looking at two examples of exponential decay. The first one involves radioactive decay, and the second one looks at decay of drugs in the bloodstream. Example 1. The amount of cobalt-60 in grams in a storage facility at time t is given by the equation C is equal to 25 times 4/5 to the power of t, where t is measured in years. We can rewrite this equation to have a base that is a decimal. And the equation is C is equal to 25 times 0.8 to the power of t. Note that if you were to use a fraction instead of the decimal, you would need to make sure that your base is expressed within brackets so that the entire base is raised to the power of the exponent. Part A says how much cobalt-60 was initially present. What we are looking for is the starting value, or the value of C when t is equal to 0. What we find is that the initial amount present is 25 grams. In Part B, it says how much cobalt remains after each year, percentage-wise. How much decays? In order to determine how much remains after each year, we look at our base value. We know that the base B is equal to 0.8. Therefore, 80% of cobalt remains after each year. To determine the amount of decay, we look at the total amount, 100%, and subtract the amount that remains. We find that 20% decays each year. In Part C, it says how much cobalt-60 is present after 10 years. This means that we want to find C for t is equal to 10. We look back to our original equation for C and substitute t is equal to 10. When we evaluate this, we find that C is equal to 2.684. We round our final answer to two significant figures, since the original amount of cobalt of 25 is given to two significant figures. Therefore, approximately 2.7 grams are present after 10 years. That means over the 10-year span, we went from 25 grams to 2.7 grams due to exponential decay. Part D says, what is the half-life of cobalt-60? In other words, what is the value of t when you have half the initial mass of cobalt-60 remaining? So you will need to determine this through trial and error, and we are going to round to the nearest whole year. We need to determine how long it takes to go from our initial amount of 25 grams until we have half of that remaining, which is 12.5 grams. So we're looking for the value of t when our amount is equal to 12.5. We can substitute 12.5 into our original equation. So we get 12.5 is equal to 25 times 0.8 to the power of t, and we want to determine the value of t that will satisfy this equation. So the value of t such that the left-hand side is equal to the right-hand side. From Part C, we know that it is for sure much less than 10 years because after 10 years you only have 2.7 grams remaining, and we're looking for the value of time when we have 12.5 remaining. So we can examine small values such as t equals 2, t equals 3, t equals 4, and examine those resultant values. For t equals 3, we get 12.8 grams, and for t equals 4, we get 10.24 grams. Remember, we want to approximate our number of years for the half-life to the nearest whole year, so we would find that at t equals 3, it is closest to our half-life. Therefore, our half-life is approximately 3 years. Now pause the video and practice, as the following example is very similar to the one that we looked at, radioactive decay. So in this example, we have a patient is given 250 milligram dose of a prescription drug to relieve pain. The amount A of the drug in the bloodstream for any time t in hours is represented by A is equal to A sub 0 times 0.78 to the power of t. Part A says, what is the value for A sub 0? So A sub 0 is the initial amount of drug present, which we know is 250 milligrams. Part B says how much of the drug to the nearest milligram is still in the bloodstream after 30 minutes. Remember, time is given in hours in this problem. Therefore, if we're wanting to know what happens after 30 minutes, we must substitute t is equal to 0.5. So we are looking for the value of A when t is equal to 0.5. Evaluating this, we find that A is equal to 220.79 after 0.5 hours. Therefore, approximately 221 milligrams remain after the 30 minutes. Part C says a second dose can be safely administered once there is less than 50 milligrams remaining in the bloodstream. We want to know if it is safe to take a second dose after 6 hours. To answer this question, we must investigate what the amount is present after 6 hours. In other words, we're looking for the value of A when t is equal to 6. We find that after 6 hours, there's still 56.29 milligrams remaining in the body, in the bloodstream. Therefore, it is actually not safe. We recognize that we're not ready for a second dose after 6 hours because there's still more than 50 milligrams remaining in the bloodstream. So this is the last example of exponential decay. Remember, there's lots of practice in your homework questions and the My Open Math homework quiz. So make sure you check those out and let us know if you have any questions. The next video we'll be looking at fitting equations.